So in the last class, we had a detailed discussion about the molten carbonate fuel cell, that is MCFC, and it is, if you want to classify that under the operating temperature, then it is high temperature fuel cell, because the operating temperature will be more than 650 degrees centigrade, and it goes up to 800. And when it comes to the electrolyte, it is a binary mixture of two carbonate salts, and in the molten form, because of the high temperature, it will be in the molten form. And this molten liquid electrolyte will be contained using a ceramic matrix. And advantages of MCFC: because of high temperature operation, no noble metals are required as catalysts, so reactions proceed faster. And when it comes to fuel, along with hydrogen, carbon dioxide and carbon monoxide can also be used as fuel. So as a requirement, carbon dioxide should be present. Carbon dioxide is involved in the reactions at both anode and cathode. And coming to the disadvantages, so because of the high temperature operation, the durability of the fuel cell and the associated corrosion are some of the disadvantages. And applications usually grid power generation, continuous power generation. That is because the start stop cycles consume a lot of time. So it takes almost 14 to 16 hours for the fuel cell to stabilize once it is started, when the stack is huge. For that reason, so it is best suited for continuous operation. And coming to the types, well within the molten carbonate fuel cell, there were three types. That is purely based on how the fuel is handled. So one is direct internal reforming, where the reforming of the fuel takes place inside the fuel cell in contact with the anode electrode. That is direct internal reforming. The second variant is indirect internal reforming. Reforming of the fuel takes place inside the fuel cell. However, it doesn't happen in contact with anode. That is the second variant. Third is external reforming. A fuel reforming unit is completely external to the fuel cell. It takes place outside the fuel cell, and the fuel, which is a mixture of hydrogen and carbon dioxide, is let in. So that is about the brief recap of MCFC. With that background, we shall proceed with the next type of fuel cell, that is solid oxide fuel cell, abbreviated as SOFC. Few general remarks about solid electrolyte. The most common ceramic material which is used as a solid electrolyte in case of SOFC is zirconia, zirconium dioxide, which is also known as zirconia. So it is a ceramic material which has the ability to conduct oxygen ions at high temperatures. So we are talking about the electrolyte, which is a solid material. In all other fuel cells that we discussed so far, the electrolyte was liquid. In a liquid electrolyte, ion conduction is easy and straightforward. But when it comes to a solid ceramic material, the ionic conduction is not that simple when compared to a liquid electrolyte. However, in materials such as zirconia or zirconium dioxide, especially when it is maintained at a temperature above 800 degrees centigrade, it conducts oxygen ions. So it was back in 1899. Nernst was the first person who spoke about the ionic conductivity of zirconia. So he was the one who mentioned that this zirconia has the ability to conduct oxygen ions when maintained at a temperature above 800 degrees centigrade. So that's where the research on SOFC started. So zirconia, when heated to high temperatures, transforms into different crystal structures, and that makes it possible for conduction of oxygen ions. And when it is cooled down back to room temperature, it might crack. So for that reason, in order to avoid this cracking, one is this heating and cooling should take place very slowly. That is one. Next is by adding certain dopants, this disadvantage can be overcome. So for that reason, materials such as atria is used as a dopant. So then it becomes atria doped zirconia. So our zirconia doped with atria, abbreviated as YZR. Okay, and by doping atria, certain additional features such as superior thermal properties, stability, conductivity, mechanical and electrical properties are obtained. So this is about, in general, solid electrolyte. So most of the solid oxide fuel cells make use of this zirconia material as electrolyte till date, and in order to enhance the abilities of zirconia or to overcome certain disadvantages of zirconia, it will be doped with atria. So this is about solid electrolyte. With this background, if we proceed, coming to the overview of SOFC. So as usual, if we start with the operating temperature, it is 973 to 1273 Kelvin. So usually most of the fuel cells operate from 800 to 1100 degrees centigrade. Because of this high temperature, it is classified under very high temperature fuel cell. The molten carbonate fuel cell is high temperature fuel cell. So this is very high temperature fuel cell because the temperature goes as high as 1000 degrees centigrade. Coming to the current density, it is high. So if you can recall the AFC, so alkaline fuel cell, current density was high. PAFC, phosphoric acid fuel cell, current density was moderate. Again in MCFC, current density was moderate. So coming to SOFC, current density is high. Okay, and as part of overview, coming to the electrodes, it is the base material can be zirconia, but additional components come into picture. So it could be like cobalt or nickel or strontium, lanthanum, are some of the materials that are added to zirconia to form the electrodes. So electrolyte is atria doped zirconia. Coming to the electrodes, the base material is still zirconia. However, additional components are added such as nickel and strontium or lanthanum depending upon the electrode. So Ni ZrO2 is an example of anode, and SrLaMnO3 is an example of cathode. We are going to discuss in detail about these electrodes later. And coming to electrolyte, so yttrious zirconia, YZ or YZR, and charge carrier, oxygen ions, O2 minus, water management. So the water that is generated is usually evaporated, and steam, in the form of steam, it comes out with the other gaseous products. Advantages: so high efficiency, flexibility of solid electrolytes, meaning there are no issues with orientation of the fuel cell. Just because the electrolyte is a solid material, it can be made as thin as possible, and there are no issues with orientation of the fuel cell. You can keep it the way you want according to the requirement. So however, when it comes to a liquid electrolyte, the orientation might play a role. And because of the solid electrolyte, there is no corrosion because of electrolyte. Of course, there is other correction, other corrosion because of high temperature, but not because of the liquid electrolyte. Okay, and again, coming to the disadvantages: corrosion due to high temperature. So even though it is termed as corrosion in both the cases, so the impact on the material will be different. So is the associated durability. And because of these high temperatures, and it is not good for the fuel cell or the material to suddenly increase the temperature to such high values. So the heating should take place gradually. Because of this, the startup will be long, and also the start stop cycles. So these are some of the disadvantages of SOFC. Coming to the applications, because of this high temperature and longer startup and start stop cycles, it is best suited for continuous power generation, usually grid power generation. So large quantity power generation is the main application of SOFC. So of course, recently researchers have explored the possibility of using SOFCs for other applications as well, but mainly it is known for power generation, large scale power generation. Okay, so with that, let's find out more information about the components and the reactions involved. One of the advantages of SOFC as discussed is because of the solid electrolyte, the phases involved are only two, solid and gas. But when it comes to other fuel cells, especially the electrode electrolyte interface where the reaction takes place, three phases will be involved: liquid electrolyte, solid electrode, and gaseous fuel. But in case of SOFC, only two phases, solid and gas. Definitely, it is advantageous when it comes to handling. And because of high temperature operation, there is no need of noble metal catalysts. Similar to MCFC, when it comes to fuel, hydrogen as well as carbon monoxide can be used as fuel. And first mention of this solid ceramic material which have the ability of ion conduction was back in 1899, and that was by Nernst. And conventional SOFCs still use the zirconia or ATS stabilized zirconia as electrolyte. So now Coming to the reactions. So the presentation is visible, right?
Yes, sir.
Okay, coming to the reactions. When hydrogen is used as fuel at anode, hydrogen reacts with O2 minus, forming water, and electrons are liberated. So those electrons move through the external circuit and reach cathode. At cathode, the oxidant oxygen gets reduced by accepting the electrons, regenerating O2 minus ions. So these O2 minus generated at cathode is conducted through the electrolyte, and finally it reaches anode where it is consumed. So this is the case when the fuel is hydrogen. And if we look at the reactions, when carbon monoxide is the fuel, so instead of hydrogen, that carbon monoxide combines with the O2 minus, forming CO2, and electrons are generated. So these electrons pass through the external circuit. These electrons are accepted by O2. O2 gets reduced, forming or regenerating O2 minus. The same O2 minus reaches anode through the electrolyte. This is about the reactions. Just because carbon dioxide is not a requirement with respect to reaction like MCFC, the process is much simpler. So if you remember, in MCFC, the carbon dioxide was essentially part of the reaction. The carbon dioxide that was generated at anode was supposed to be separated and sent back to cathode. So additional step was required, additional equipment was necessary, such as separators, or it could be a membrane separator or a combustor. So such requirement is not there in SOFC. This is about the reactions. To proceed further, little more information about the electrolyte. YZ, yttrious zirconia. In some places, it is mentioned as YZR as well. E is the most common electrolyte. It is highly stable in both the reducing as well as oxidizing environments, because at one side of the electrolyte, so the oxidation reaction takes place, and at the other side of the electrolyte, reduction reaction takes place. So it will definitely, the type of the reaction will definitely have an impact on the material. So this material is stable in both the environments, and the main role of electrolyte is to conduct ions, and until and unless it is comparable or better than the liquid electrolytes, a solid electrolyte cannot be used for the purpose in a fuel cell. However, in this case, the ion conduction is comparable with the liquid electrolytes, so it can be used as an electrolyte. The next thing is, because it is solid electrolyte, the thickness can be reduced to a maximum possible extent. So it will be in the order of microns. So if you look at the thickness of a solid electrolyte in SOFC, it is as thin as 40 microns. So it can be anywhere between 40 to 60 microns. Coming to the method, how it is fabricated. So tape casting, as discussed in case of MCFC, the same holds good here as well. Another method is electrochemical vapor deposition, EVD. So CVD is chemical vapor deposition, electrochemical vapor deposition is EVD. So this is another technique with which electrolytes as thin as 40 microns can be fabricated. Usually, depending upon the type of fuel cell and the operating temperature, the associated losses, the magnitude of those losses will vary. Likewise, in SOFC, there are no losses, or I would say the losses because of the reactions, the activation losses are very little, because the operation is at high temperature. Because of the such a high temperature, reactions proceed faster, and also that eliminates the requirement of noble electrocatalysts. However, losses due to resistance, which are termed as ohmic losses, are more in case of SOFC, and that mainly depends on the thickness of the electrolyte. So what are these ohmic losses? We definitely are going to discuss this in detail in unit 3, but for your information, ohmic losses are losses because of the resistance offered by the material for the flow of electrons and ions. So here the thickness of the electrode as well as thickness of the electrolyte plays a major role. Only way to bring down the loss because of this resistance is to keep both electrodes, electrolytes as thin as possible. Because it is a solid electrolyte, we can definitely make it very thin. Because of that, the losses due to resistance can be drastically reduced. And along with this YZ, or along with Atria, little alumina is also added in some cases, which provides additional mechanical stability to strengthen the electrolyte. The other variants with respect to the electrolyte material are CeO2 and Bi2O2. They show higher oxygen ion conductivities, but they are not very stable at these high temperature operations. So research wise, different materials are explored. However, till date, the electrolyte that is used in commercially available SOFCs are still YSZ, that is AT established zirconia. And this is about the electrolyte. Coming to the electrodes. So let's start with anode. Usually these electrodes are cermets. So have you ever heard of this word cermet? Do any of you know what is this?
No, sir.
Okay, mechanical engineers would be mechanical engineers. Have you ever heard of cermets? Okay, you know composite materials, right? Usually in case of composite materials, there will be a matrix material and a reinforcement. So likewise, these cermets are also composite materials where the reinforcement is metal chunks and the matrix material is ceramic material. So cermet, as the name indicates, so CER represents the ceramic part, MET represents the metal part. So that's how the name cermet. is a composite material made of metal reinforcement and ceramic matrix. So the matrix material is zirconia. Coming to the metal, in case of anode, nickel is used. So this has an added advantage. Before going to that advantage, how does these cermets work? So ceramic material is usually uh, not known for conducting ions. So if metal chunks are added in between, that enhances the conducting property. And because of high temperature operations, especially this zirconia, which already has this ion conduction ability, will be further enhanced because of addition of nickel. Now coming to the another advantage of having nickel is this nickel acts as catalyst for reforming reactions. So taking this MCFC as an example, we got to know about a variant of MCFC where internal reforming is a possibility. Fuel other than hydrogen, such as hydrocarbons or natural gas, will directly enter the fuel cell. The steam reforming of hydrocarbons takes place well within the fuel cell. So the same thing is applicable in SOFC as well because of this high temperature operation and presence of nickel material inside the anode electrode. It further enhances the steam reforming reaction because nickel is one of the catalysts that are used in steam reforming reactions. So it is an added advantage in case of SOFC. So direct internal combustion is an option where the steam reforming of the fuel happens in contact with anode. And coming to the porosity, so it will be in the order of 20 to 40%, just to make sure that there is no hindrance to the flow of the gases. And ceria is a material that can be added as a dopant when it comes to fabricating or manufacturing of these anode electrodes, which improves the tolerance to temperature cycling. So what is this temperature cycling? It is nothing but the changes in temperature because of start stop cycle. So the material should reach a temperature of 1000 degrees centigrade all the way from room temperature. Again, for reasons if it is stopped, so it will be cooled back to room temperature. This is known as temperature cycling. Stability or tolerance with respect to temperature cycling is enhanced when ceria is used in fabricating these electrodes. And the particle size will also play a role, and control of particle size can definitely improve the stability of the anode. There are other variants based on titania, that is titanium dioxide, which are known to promote direct oxidation of methane when methane is used as fuel. This is about the anode of SOFC. So coming to cathode, the fabrication or handling is not that straightforward like anode. So usually electronic property is encased here. One general requirement is it should be definitely porous, highly porous, which can enable rapid mass transport of gases. Usually cathodes are made of electronically conducting oxides or ion conducting ceramics or semiconductors. Semiconductor materials are usually used for cathode materials. One common example is strontium doped lanthanum manganate is a common cathode material. Other variants or examples are p-type conducting materials, especially perovskite materials, and which have the ability to exhibit ionic as well as electronic conductivity. This will further enhance or help in bringing down the losses due to resistance, that is ohmic losses. And there are examples where n-type semiconductors are also used. That is about the cathode of SOFC. Now coming to the design, are types or variants within SOFC. So there are actually three variants. One is the planar design, where the electrolyte assembly is completely planar, sheet-like structure, thin sheets, that is planar design. The next variant is monolithic design, so which looks like honeycomb, or honeycomb structure is made use of. The materials, that are the components, the electrodes are casted in the form of the honeycomb, and that is the monolithic design. Third one is tubular design. Depending upon the application, the design is selected. So both planar and tubular designs are popular. And getting into more details of this tubular design, so it was first experimented in 1970s. So what happens here is the electrodes and electrolyte are concentric tubes. In the original design, support tube made of calcium stabilized zirconia was used. On top of that, the anodes were tape casted. But later, in the recent current tubular designs, the innermost tube, the base tube is cathode material. On top of cathode, the electrolyte is casted, and on top of electrolyte, the anode material is casted. So what is this procedure? The cathode material is casted in the form of a tube. So such tube is considered as the base material. On top of that, the electrolyte material is grown on the cathode tube. So what they do is, this electrochemical vapor deposition takes place on top of the cathode material, cathode tube. Once the required thickness is obtained, the anode layer is fabricated on top of the electrolyte. So as the innermost tube is cathode, air, the oxidant, is circulated through the inner tube, and the fuel is circulated outside, as anode is the topmost layer. And this part here is the interconnect, which is very similar to bipolar plate. So in case of conventional planar design, bipolar plates are used as interconnects. But when it comes to tubular design, so this is how the interconnect looks like, which connects the cathode of one cell with anode of another cell. That is how stacking is done. And electrolyte interconnect and other electrode are deposited by the process of masking or tape casting or EVD or CVD. And this is how the cross-sectional view of tubular design looks like. So this is how a module, a stack of multiple tubular SOFCs look like. Of course, with every design there will be certain disadvantages. So here the power density seems to be little low and the fabrication costs are high. These are some of the disadvantages of tubular designs. And in the very initial designs, support tubes made of zirconia were used. So those support tubes are eliminated. The cathode tube itself will act as a support tube. And other components such as high temperature gas tight seals were required in earlier designs. Those are also eliminated. So this is a commercially available SOFC, which consists of 1152 individual fuel cells that are stacked together, which can generate a power of 200 kilowatt. So whenever these larger stacks are required, usually a module that consists of fuel cells from 16 to 24 are made, and such modules are clubbed together or bundled together to make larger stacks. So in this case, so 24 individual SOFCs are connected together to form a module. Such multiple modules are connected to form larger stack. So this is one such example where 1152 fuel cells are stacked together, which can generate a power of 200 kilowatt. And especially when it comes to the power plants based on SOFC, definitely there are other components that are necessary along with the fuel cell module. So this we had discussed in the very beginning itself when it comes to BOP, that is balance of plant. And also because of the high temperatures involved, the steam that comes out at a very high temperature can definitely be utilized to generate power further by running turbines, so which is known as CHP. And usually when it comes to BOP, the fuel cell stack is the central unit, and depending upon how the fuel is processed, if it is an external reforming of fuel, then an additional reforming unit is necessary. And of course there are many converters involved. The thermal management system is required. A typical dimension of such a unit will be somewhat like 9 by 3 by 3 or 8.5 by 3 by 3 meters in dimension. So this is how a typical SOFC CHP unit looks like. Now coming to the planar design. So planar configuration and monolithic designs are the alternatives to tubular design. The stacking arrangement is very similar to the other fuel cells such as PEMFCs or PAFCs in case of planar configuration. In planar configuration, bipolar plates are necessary, but when it comes to tubular design, it will be an interconnect. And usually the losses that dominate in SOFC as discussed are ohmic losses. So in order to bring down those ohmic losses, the electrolyte is made as thin as possible. However, to compare between the designs, so the bipolar plate design offers very little resistance. So the losses due to ohmic resistance, ohmic losses are low in case of bipolar plate design. And stack performance is also very good, and power density is high. So if you remember, in case of tubular design, one of the disadvantages was low power density that can be overcome when the planar design is used. And low cost fabrication techniques such as screen printing and tape casting can be used when it comes to fabrication of planar SOFCs. So every method will have advantage as well as disadvantage. So the use of the seals, the gas tight seals are eliminated in tubular design. However, the power density is low, but here the power density is high, but we will end up using the gas tight seals. So this is about the advantages and disadvantages of SOFCs. Any questions so far? Okay. So with this, we shall end today's session, and in the next class, we shall continue with the next type, that is PEMFC, and coming to the portions of